Okay, this question is about magnetic fields, particularly a magnetic field flowing through a wire. I can only show you the one screen, so I'm going to move away from this diagram, but this is the diagram that you need to be using for this question. The actual questions are on the next page. Part of the wire from A to B is viewed from above. Direction of the current is out of the plane of the paper, which is shown here by the dot in the middle. Using the diagram, draw the magnetic field pattern due to the current. Okay, so for this one, you want to use your right-hand rule with the bent fingers, the kind of right-hand claw rule. So your thumb is the direction of the current, and your curved fingers are the direction of the magnetic field. So the magnetic field is going to be going around like that. And the magnetic field decreases as you get further away, so the circles are going to be the distance between the circles is going to be increasing as you get further away from the center. Deduce what happens to the reading on the electronic balance when the current is switched on. Okay, well, if we look back at the diagram, then we can see we've got two wires, and here is the electronic balance underneath. So we want to know what's going to happen to this wire, what force is going to... The lower section is the wire that's on the balance, so we need to know what force that is going to experience. So if we have... if there's two ways to think about this. First of all, if you could try drawing the two wires. If you draw the two wires, then you have one coming out of the page and one going into the page, and you draw the field lines around them. I'll do it in a different color. Then the field lines are going to look something like this. Okay, and then as you add other field lines, they have to squeeze into a smaller and smaller space in the middle there. So there's a high concentration of field lines in this area here, which means that they're going to try... Field lines kind of behave a bit like elastic bands. If you squash too many of them together, they're going to push out. So these ones are going to repel from each other, which is going to mean that if the wires are repelling each other, then this one's going to be pushed up, this one's going to be pushed down, which is going to increase the reading on the balance. So that's one way to explain it, using a diagram like that. The wires repel each other, so the balance reading increases. The other way is you can use the left-hand rule. So you can say, well, the magnetic field from this top wire is going to be going, if you use your right-hand rule with the curved fingers again, the magnetic field from this top wire is going to be going into the page at this bottom wire here. So we're going to have a magnetic field that's something like that. Let me change color so you can see it a bit better. Down here we're going to have a magnetic field going into the page. So if you use your left-hand rule for the motor effect, then you have your first finger, your index finger for the field, which is going into the page, your second finger, your middle finger for the current, which is going from right to left, and so the thumb, your force, is pointing downwards. So you've got current, field is going in, and so the force must be going downwards. So that's your increased reading on the balance. So that's two different ways of doing it. So you can use the left-hand rule from the field due to the top wire, means the force is down, so balance reading increases. Or you can use this diagram and say the wires repel, so the force is down, so balance reading increases. Okay, so two different ways to think about the same question there. Okay, when the current in the wire is 0.2 amps, the magnetic field strength at the upper section of the wire due to the lower section of the wire is that. Calculate the magnetic force acting per unit length on the upper section of the wire. Well, we've got a simple equation for this, F equals BIL. And we want the force per unit length, so we want to find out F divided by L, which equals BI. You're given both of those two things, so 0.2 times 1.3 times 10 to the minus 4 gives us an answer of 2.6 times 10 to the minus 5 newtons per meter. C part 2, each cubic meter of the wire contains approximately that many free electrons. The diameter of the wire is that. deduce the speed of the electrons in the wire when the current is 0.2 amps. So we're after the speed of the electrons. Now the key thing here, there's an easy way to do this and there's a slightly more complicated way to do this. However, the question says using the force per unit length calculated in C part 1, which suggests that you might need to do the more complicated way. So I'm going to do both here. I'm going to divide this up. First of all, the easy way is to use your drift velocity equation. So I equals NAVQ. N is the number of charge carriers per unit volume, which is 8.5 times 10 to the 28. We're trying to find V, so V equals I over NAQ. The current is 0.2 divided by the number of charge carriers, which per unit volume, which is 8.5 times 10 to the 28, times the area, the cross-sectional area of the wire. If it's got diameter of that, then that's pi times 2.5 over 2 squared, times by Q, which is the charge on one of the charge carriers, which is 1.6 times 10 to the minus 19. And that gives you an answer of 3.0 times 10 to the minus 6 meters per second. That's one way of doing it, but we haven't used the force per unit length calculated in C part 1. So I imagine you would lose a mark for that in the mark scheme. So what I'm going to do instead is I'm going to say, well, the volume is pi. The volume of the wire in the field is pi times d over 2 squared times the length. That's the volume of the wire in the field, which works out as 7.36 times 10 to the minus 7 meters cubed. That's the volume. We know that there are this many charge carriers in unit volume, so we need to do 8.5 times 10 to the 28 times 7.36 times 10 to the minus 7, which will give us the number of charge carriers in that volume, which is 6.256 times 10 to the 22 electrons. That's how many charge carriers there are. We need to then, if we're going to use the force, then the force, the equation for force, which takes into account the velocity of the charge carriers, is F equals BQV. Q is not the number of electrons, Q is the charge in coulombs, so we need to figure out how many coulombs that is. So we need to do that. Let's do a different color. We need to do that multiplied by 1.6 times 10 to the minus 19 to give us the charge that many electrons has, which gives us a charge of 1 times 10 to the 4 coulombs. That's the charge within that section of wire. Here we've got, we want to figure out the velocity, so V equals F divided by BQ. The force we calculated up here, this is what it's saying we need to use in the equation. So the force is this, but remember this is force per unit length, so we've got to times that by the length. So the force there is 2.6 times 10 to the minus 5 times 0.15, because that's no longer force per unit length, and that's just force. Then divide by the field strength, which is 1.3 times 10 to the minus 4 from the top of the question, times Q, which we've just worked out, which is 1 times 10 to the 4, and that gives you also an answer of 3 times 10 to the minus 6, but that is using the force per unit length calculated in C part 1. So I imagine this method would get you 3 out of 4, and this method on the right hand side would get you all 4, because you've used the force like you were told to. Okay, question D. The upper section of the wire is adjusted to make an angle of 30 degrees with the lower section of wire. Outline how the reading of the balance will change, if at all. Okay, well, there's two things that you could say about this as well. First of all, the full equation for this would be F equals BIL cos theta. That would be the force on the extra force on the top hand balance. Obviously, that's dependent on the angle. So as theta increases from 0, F would decrease. so the reading decreases as well. The other way to think about that is that if you've got your wire here and your magnetic field from your other wire is in circles like that, the further away from the other wire that you get, the weaker the magnetic field. So if the magnetic field is weaker, if B is weaker as you get further away from that other wire, then the force is going to be weaker as well. So if you have the wire is an angle like that, then this bit, which is further away from the wire, would experience a smaller B, and so therefore a smaller force. So that's the other way of explaining it as well.